Let's look at two new thermodynamic functions, the Gibbs function G and the Helmholtz function A. Both of these functions are going to play important roles in thermodynamics. So let's look at both of them. So we're going to define these in a similar way that we find enthalpy. Remember we said that if we took internal energy and added a PV term to that, that's how we defined enthalpy. We're going to define G and A in a similar way. We're going to say if we take internal energy and subtract the product of temperature and entropy, that's going to be the Helmholtz function. That's the definition of the Helmholtz function. And we can do the same thing, or a similar thing, to define the Gibbs function. It's going to be just enthalpy minus Ts. So these are just definitions, and it turns out that by defining these functions this way, these functions are going to have a lot of convenient properties in thermodynamics. We already saw that by defining enthalpy the way we defined it, it ends up having a special relationship to heat, right? That delta H is equal to heat if we're working at constant pressure. Well, we're going to find out that there are important properties of the Helmholtz function and the Gibbs function as well as a consequence of the way that they're defined. Let's look at the differential form of these functions. As we've seen, the differential form is the easiest way to work with these functions since we're often interested in changes. Let's start with the differential form for du. And one form that we all know is just the first law. Work plus heat is equal to the change in U. We can rewrite this in terms of state functions. If we're working reversibly, then we can replace work with negative PdV. And we actually have to say not just that we're working reversibly, but also there's only PV work. Right? We don't have any electrical work because we're just including expansion contraction work here. So we have dq. Now dq is not a state function. It would be nice if we could get rid of this dq and replace it with something that's a state function. Let's pause here and say, wait a second, if it's reversible, if we're looking at reversible processes, then we can say that ds is equal to dq over t, if we're working reversibly, and we stated over here that we were. So we can multiply through by dt and get dq is equal to t times ds. Now we have an equation for dq that we can plug in up here. So we'll just put that in right there, and we'll get that du is equal to negative pdv plus tds. And this is a new equation for the change in internal energy. And the nice thing is it's made up only of state functions. So we say that the natural variables of u are going to be the variables that change u. That would be the volume and the entropy. So we say u is a function of volume and entropy. We can go through a similar exercise with enthalpy. We said enthalpy is equal to u plus pv, or dH is equal to du plus pdv plus v dp. Now we already said that for reversible situations du is equal to negative pdv plus tds. Now that's just du in disguise. So now we throw these other terms on there, and we can see we could cross off these, and say that, oops, this morphed into, this is dH here still. We can say that the change in enthalpy is going to be TdS plus VdP. So we can see that the natural variables of H are, well, what are they? Okay, so we know that there's these variables here that cause the change. So it's going to be entropy and pressure. Let's do two more. Let's do the Helmholtz function. We said the Helmholtz function was defined as U minus Ts. So the change in the Helmholtz function is a change in U minus TdS minus STT. We already have an equation for du minus PdV plus TdS. Throw in these other terms. Oops, they're negative. And we can see the TdS cancels. So we get that we can calculate the change in Helmholtz function from the change in volume and the change in temperature. So the Helmholtz function has natural variables volume and temperature. Now, this is significant because volume and temperature are things that are easy to control in a lab. And so for situations where we have constant volume and constant temperature, we'll see that the Helmholtz function plays a very special role. So once again, this is an important equation, and the only restriction on it is that for this to be an equal sign, this has to be a reversible process. So reversible processes have this function here for any system. Finally, the most important is the Gibbs function. So the Gibbs function is equal to the enthalpy minus Ts. So we have the change in the Gibbs function. It's a change in the enthalpy minus TdS minus STT. We saw that the change in the enthalpy, TdS plus VdP. So when we add these other terms on, we can see that we can cancel the TdS terms, and we get that the Gibbs function is VdP minus STT. This equation is probably the most important equation for the rest of the quarter because it tells us how the Gibbs function varies with pressure and temperature. And we can see from this that Gibbs function has the natural variables pressure and temperature. And what this means, we'll see later, is that in situations where we're holding the temperature and pressure constant, the Gibbs function is going to be very significant. And as you can imagine, we often run reactions at constant pressure and temperature. And so for us, the Gibbs function is probably the most important function in thermodynamics.